Okay, so in this webinar I'm going to be talking about how we can go about computing X-ray absorption spectroscopy with Q-Chem. And I will give an introduction to X-ray absorption spectroscopy and tell you a little bit about the technique and why people want to use it. And then I'll focus on using time-dependent density functional theory to compute X-ray absorption spectroscopy. And the way I've organized this is we're going to start at considering a normal time-dependent density functional theory calculation where we're just looking at valence excited states. So this is a sort of calculation which I expect most people will have done before, and then demonstrate how the input is modified to compute core excited states, and also try and give a bit of background behind why we do things, and in particular looking at new exchange correlation functionals which have been designed for the calculation of X-ray absorption spectroscopy. So X-ray absorption, so if you, in the X-ray region, you begin to see spectroscopy of the core electrons. So if you shine sufficient light, sufficient energy at your molecule or sample, you can ionize core electrons. And this would be X-ray photoelectron spectroscopy, where you're just ionizing the core electron. Once you've created this core hole, you can then get emission spectroscopy as your occupied valence electrons, orbitals, decay back down to fill the core hole. And this can be coupled in a 2-electron process, such as in Auger spectroscopy. The bit we're focusing on is near-edge X-ray absorption fine structure, and that's where you're exciting your core electron to some low-line virtual orbital to produce a state below the ionization threshold. And in many senses, this process is very similar to a normal electronic excitation, but it's just occurring at much higher energy. And it's in that spirit that we should be able to compute these things accurately with something like time-dependent density functional theory. So I often refer to this as NEXAFS spectroscopy, but it's also referred to as something as XANES, which stands for X-ray absorption near-edge structure. And here is a schematic of what a spectrum would look like. And so this is the absorption edge. That's where you begin to see excitations of your core electrons. And the bit we're interested in is this structure near the absorption edge, and that's called the near-edge X-ray absorption fine structure. At higher energies, you get this slowly oscillating structure, and that's extended X-ray absorption fine structure. And the methods I'm talking about today are not really designed to compute this bit. We're focusing on this near-edge region. And the other thing to get sort of the notation right is if we talk about K-edge excitations, we're dealing with excitations from 1s orbitals, and if you're interested in excitations from the 2p orbitals, that would be called the L-edge. And again, in this talk, I'll be focusing on the K-edge excitation. So that's I'm thinking about excitations from 1s orbitals. Now, NEXAFS is in principle similar to the normal UV absorption spectroscopy, but there are a couple of differences. The first is that the transitions are going to be at much greater energy, and so the experiments for these types of measurements will be done at synchrotrons. But the advantage of these techniques is they're element specific, and that's what I'm trying to illustrate here. And this is just showing you the difference in energy between the different absorption edges, whether you're thinking about exciting from a boron 1s orbital, where this edge is around 200 electron volts, the carbon 1s orbital, which is about 285 to 290 electron volts, then the nitrogen 1s orbital, which is sort of 415 electron volts. And so because these different excitations are so far apart in energy, that means you can focus in just on looking at carbon 1s excitations. So you can focus in just on the carbon part of the spectroscopy. And then similarly, so if you want to look at excitations from the nitrogen 1s, you're talking about a different experiment to do that. And this is actually quite a powerful advantage for these types of techniques. Okay, so NEXAFS is used in many areas of science. A classic area is in surface science, where looking at polarized X-ray light, you can begin to say things about how your molecule is absorbed on a surface. There's been high-profile experiments looking at liquids, and those of you which are up to date on these sort of experiments is that by looking at near-edge X-ray absorption fine structure and also X-ray emission spectroscopy, it was proposed that water sort of deviates from its liquid water sort of deviates from its normal tetrahedral type coordination, and this is a big ongoing debate in the literature. But fundamentally, it was started with NEXAFS experiments. Also, materials science, looking at defects, things like that, can be done with NEXAFS spectroscopy, and also in biology. So here, where this has been used predominantly is looking at metalloproteins, so using NEXAFS spectroscopy to say something about the bonding in your at your metal center in your metalloprotein. Okay, so the ultimate objective of what we want to achieve with these calculations is we want to perform accurate calculations of near-edge X-ray absorption fine structure of large systems. So what I mean by accurate is, when we think about UV excitations, we sort of think about trying to get things within 0.3 electron volts. So as we go to the X-ray region, we'd like to be able to sort of maintain that level of accuracy. We might not achieve it, but that's kind of, if we could get these things within 0.3 electron volts, and I think that's as good as you could ever really expect to achieve. And in terms of the size of the system, an example like coronene, where we're looking at excitations from the carbon K edge. And this is actually, once you look at the NEXAFS spectroscopy of this system, it's actually quite an expensive calculations for a couple of reasons. Firstly, you're looking at, you've got a large number of carbon 1s orbitals, which you'll be looking at excitations from. And also, when you look at this type of spectroscopy, the actual density of the transitions is much higher. So to actually cover a spectral range of about 10 electron volts from the absorption edge, you actually have to compute many more routes than you would have to do for a typical calculation in the UV region. And that will become clearer as we go on through the talk. So our first example is to just look at computing the UV spectrum for a simple molecule like formaldehyde, and we're going to use a range-corrected functional CAM-B3-lip. And so this is how a typical Q-Chem input would look. And so here you have to define the charge and multiplicity. You have to give the coordinates. Here I've given Cartesian coordinates in angstrom. Then you have to tell Q-Chem which functional you want to use. You have to specify your basis set. And then to do the time-dependent DFT calculation, you have to tell the Q-Chem how many routes you want to compute. So in this calculation here, I'll be computing the lowest 10 routes. By turning CIS triplets to false, that means we're not going to compute triplet states, we're just going to compute singlet states. And then by turning RPA to false, that means we're going to be doing a time-dependent density functional theory calculation within the Tamm-Dankoff approximation. And you can go on to do full time-dependent DFT calculations if you set this to true. And if you run a job like that, and then you look at your output, this is the bit we're interested in, which is where it's printing out the excited states. And so these are our transition energies in electron volts. This is the multiplicity, then this is the oscillator strength, and then these bits here describe essentially the transition that corresponds to this excitation. So this notation says that this excitation corresponds to exciting electron from the 8th doubly occupied orbital to the first virtual orbital, the first unoccupied orbital. And you get lots of these states, And so this second transition is at higher energy, 7.2 electron volts. This is its intensity, and now we're exciting from the 8th doubly occupied orbital to the second virtual orbital. And then you can actually look at what these orbitals look like. In Q-Chem will produce some input for the Molden program, or you can do it through Spartan. And so this is what the 8th doubly occupied looks like. It's would be called essentially a lone pair, associated with a lone pair on the oxygen atom. And this is the first virtual orbital. So this is the pi star orbital. So this transition would be an end to pi star transition. And then you can look at these higher states, and you can put these correspond to excitations to Rydberg states. This would be an N to 3s transition, N to 3p Rydberg, and another 3p Rydberg state. Okay, so that's really what we do for valence transitions, and I suspect most people would be fairly comfortable with doing those kind of excitations. So did it change? So a second example is if we actually want to extend this to compute core excitations. So what I'm after is doing a calculation where we look at exciting from the carbon 1s orbital to this pi star orbital, or the oxygen 1s orbital to this pi star orbital. And again, we're looking at formaldehyde. So you should now see a new input. Okay, so all I've done in this input is change the number of roots. Okay, so these excitations are going to be much higher energy. So to actually get those, we're going to have to ask our calculation or our code to compute far more roots than we did before. And you can run this calculation and you can see. So if you actually look at excited state 205, this is the excitation energy. It's much higher, 275 electron volts. And if we look at the transition, it's from the second doubly occupied orbital to the first virtual orbital. And then this orbital here is the carbon 1s orbital. So this is our carbon 1s to pi star excitation. And similarly, here, if you look at excited state 239, this lies at 517 electron volts, and this is from the first doubly occupied orbital, that's the one with lowest energy, to the first virtual orbital, and that corresponds to the oxygen 1s to pi star excitation. Okay, but you can see that as soon as you move to a larger molecule or use a larger basis set, then this type of approach is just not tractable. Okay, you're going to have to ask for so many roots that your calculation will soon become prohibitively expensive. Okay, so you need to make some simplifications to actually reduce the cost of these. And the way we do it is to essentially do our time-dependent density functional theory in a reduced excitation space. And I'm going to talk through examples of that now. So what we want to do is just say, all we want to do is compute excitations from the carbon 1s orbital. Okay, and so again, this is our input formaldehyde, can be free lip. So all this up to here was what we had before. Now we've added these extra bits of input, and what this is doing is just telling our time-dependent DFT calculation just compute a subset of the electronic excitations. So we turn on this keyword TRNSS, which is meant to stand for truncation of the single excitation space, turn that on to true. We select this truncation type to be free, and by doing this, what it will do is just include excitations from the orbitals specified to the complete unoccupied space. And so in this calculation, I specify this n sols 1 because all I'm interested in is excitations from the oxygen 1s orbital. So I'm just going to compute excitations from a single orbital, which is the oxygen 1s orbital, and that orbital is specified in this list here. So this is saying compute excitations from orbital 1 to the complete virtual space. Okay, so we'll see lots more of these inputs as we go through, so hopefully that'll become clear what's going on there. So if you run this calculation, you'll see this extra bit in the output, which is telling you you're doing a TDDFT calculation in a reduced excitation space. And so this is telling you the orbitals which are in your truncated space. And so you can see we've got 1 here. That's the orbital we've specified. So we include orbital 1 is an occupied orbital, so we're including the first occupied orbital. So our occupied orbitals, we've got 1 out of 8 which we're including, and then all of these 34 orbitals are our virtual space. Okay, so this calculation should just do calculations from orbital 1, which is our oxygen 1s orbital, to the complete virtual space. Okay, and then if you look at the output you get, here we can see now we're doing excited state 1. If you remember back to when we did this, including all excitations, I think this was excited state number 239. Now it's excited state 1. Okay, excitation from our first doubly occupied orbital to our first virtual orbital. So this is carbon 1s to pi star, and this is our energy. And if you compare those numbers with what we got before, you see the energy's virtually the same, and also the oscillator strength is pretty much bang on as well. Okay, so you can see by doing this, we're getting the states we want. All we're getting is the states we want. We don't have to compute all these other states which we're not interested in to get to the core excitations which we are interested in. I mean, the reason why this number is so close to this number is because the core orbitals are so far separated from the other occupied orbitals which we've excluded that there's actually so little mix in between them in terms of when we do our time-dependent DFT calculation that this number actually comes out so close. So although this is an approximation to do this truncation, it's actually quite a good approximation, and you know the errors you're getting by making this approximation are just tiny compared with other errors which we're going to see as we go on. Okay, so if you wanted to change this to do the carbon 1s orbital, we'd have exactly the same thing again, except now we specify the second orbital, which is the carbon 1s orbital. So these orbitals are labelled in terms of their energy, with the lowest energy one being orbital 1. Okay, so often if you're doing these things, especially if you're going to have to include excitations from more than one core orbital. So here's an example if we're thinking about doing the same type of calculation where we're thinking about the K-edge for a molecule like benzene. So again, here's our input. We've got coordinates, Cartesian coordinates. We have to specify the number of roots. As we'll see a bit later, if you want to compute a whole spectrum, you're going to have to ask for quite a large number of roots. So the difference here is I'm including all 6 carbon 1s orbitals. So I have to change n sol to be 6 because I'm including 6 carbon 1s orbitals, and I have to tell them what they are. Their numbers 1, 2, 3, 4, 5, and 6. The lowest 6 orbitals in this molecule will be the carbon 1s orbitals. Again, you can run that calculation, and you can see this is what we get. So now in our orbital subspace, we've got our first 6 orbitals. So we've got 6 out of 21 occupied orbitals. They're our carbon 1s orbitals, and we're exciting into our complete virtual space. And I'm just picking out one transition here, and so this transition here corresponds to essentially a carbon 1s to pi star transition in benzene. And if you look at the NEXAFS spectrum for benzene, there's a very strong peak which corresponds to this transition. Okay, and that's really what we're picking out here. Of course, when you do this, you'll have lots of other transitions. So the first 6 transitions will correspond to carbon 1s to pi star excitations, but only this one has really got significant intensity. Okay. So that's how we actually go about it. So now let's think about what is the accuracy of these computed excitation energies. Here I've told you, or can-be free lip is telling us that the carbon 1s to pi star transition in benzene is 275 electron volts. Is that a good number or a bad number when we compare it with experiment? And so here are some numbers. So these are just some transitions not chosen for any particular reason, where we've got a carbon 1s transition in carbon monoxide, the oxygen 1s to pi star, and then the fluorine 1s to sigma star. And these are experimental numbers, and these are the numbers you get if you do a B-free lip calculation, and these are the numbers you get if you do a can-be free lip calculation. Here I'm using a bigger basis set. But the thing to notice is these numbers are much lower than the experimental numbers. Okay? And that the amount at which it underestimates actually increases as you increase the nuclear charge, or as the nuclear charge of your nuclei, where the core orbitals localized, increases. So that's the first thing I want you to notice, is these numbers are too low. And the second thing I want you to notice is going from B-free lip to a long-range corrected functional can-be free lip makes very little difference to these numbers. Okay. So, I mean, I'm going to build an analogy with thinking about charge transfer transitions. So most people will know that when you look at charge transfer transitions in time-dependent DFT, if you use a GGA functional, a hybrid functional, then the excitation energies tend to be too low, and that's corrected if you use a long-range corrected function like can-be free lip. And there's a diagnostic of this, which is called the lambda diagnostic, which Q-Chem will compute for you if you ask it to, which essentially measures the overlap between the orbitals you're exciting from and those where you're exciting to. And so this was work done by Dave Tozer, Trygve Helgekar, Michael Peach, and someone else. And they published this a few years ago, this lambda diagnostic. And it turns out if this lambda diagnostic is less than about 0.4, then this tells you that your GGA functional or your hybrid functional is likely to have a large error. So if we look at these numbers for core excitations, then these numbers are much less than 0.4. So this is telling us that we wouldn't expect our GGA functional or hybrid functional B-free lip to give a good answer. Okay, so the fact that this diagnostic is less than here tells us that we'd expect some problems in using our standard GGA and hybrid functionals for these types of transition. However, where we sort of begin to normally what you do if you're looking at valence transitions and you saw this type of value of lambda, is you'd switch to using a long-range corrected functional, and that would hopefully fix things for you. But we've seen already that when it comes to these core excitations, it's having very little effect going to use this long-range corrected functional. Okay, so let's recap on long-range corrected functionals, so just so that everyone is kind of can follow the arguments I'm making. So long-range corrected functionals are really a quite pragmatic idea, and I guess underlying the idea is the failure of these functionals is related to the exchange component of the functional. And so the idea of these long-range corrected functionals is just to say, okay, well we'll use DFT exchange, something like Becky exchange where DFT exchange works well, and then we'll switch to Hartree-Fock exchange, exact exchange, where DFT breaks down. And it's quite an elegant way in which it's done, is that the 1/R12 operator in the evaluation of the exchange energy is partitioned using these error functions into a long-range part and a short-range part. And for a long-range corrected functional, we treat the short-range part with DFT and the long-range part with Hartree-Fock theory, Hartree-Fock exchange. So let's think about what's happening if we think in terms of core orbitals. So our long-range corrected functional is introducing Hartree-Fock exchange when R12 is large. So if R12 is large, then either R1 or R2 has to be large. And so all of these exchange integrals, if these orbitals involve core orbitals, the thing about core orbitals is they're very short-ranged. So if R1 or R2 is large and that's involving a core orbital, then that will make this integral very small. Okay, so that's just saying because our core orbital is dying off so rapidly, you know, for large values of R, it's essentially going to be 0. So I think what's happening when we do a long-range corrected functional, when we're talking in terms of core excitations, that for these exchange integrals involving the core orbitals, where Hartree-Fock exchange is being introduced, all of those integrals will be quite small for when they involve core orbitals. Okay, so this really leads to, I guess, the key idea when thinking about computing core excited states, and that is let's turn the problem on its head, i.e., whereas a long-range corrected functional introduces Hartree-Fock exchange in the long range, let's turn it on its head and introduce Hartree-Fock exchange in the short range, i.e., where R12, the distance between our electrons, is small. So here's a simple plot where you've got the fraction of Hartree-Fock exchange. So we're going to start off when R12 is large with some higher proportion of Hartree-Fock exchange, and then that's going to decrease. It could decrease to 0, or it can decrease to some finite number. Okay, and then we're going to see, does that improve our calculated core excited states? And the details of this, really, I'd refer you to the paper, but we have essentially a way we partition our R12 operator, again in the evaluation of exchange energy, such that we can introduce a component of short-range Hartree-Fock exchange, and we can also introduce a component of long-range Hartree-Fock exchange. And this functional introduces 4 parameters. This C short-range Hartree-Fock, which is really telling you how much Hartree-Fock exchange you want when R12 is 0, and C long-range Hartree-Fock exchange, which is telling you how much Hartree-Fock exchange you want as R12 gets large, goes to infinity. And then you have a parameter, mu short-range, which is really saying how fast does the short-range Hartree-Fock exchange switch off, and then a long-range mu, which is telling you how fast our long-range Hartree-Fock exchange switches on. So what we've done is we've taken a set of core excitation energies from experiment and essentially optimized these 4 parameters in this functional. Okay. What we find is we have to treat excitations from the core orbitals of first row elements, carbon, nitrogen, etc., different from when we go to heavier elements down the periodic table, and I will return to that later on. Okay, so does this thing work? So here are our computed excitation energies again, and so here you can see these are what we get from experiment. You can see now these numbers match up much closer than what we got before. When we look over a larger set of excitations, we get an average error of about 0.3 electron volts for first row nuclei and slightly more for second row. Okay, but the point is that we're now sort of at a sort of accuracy level which we typically expect if we're looking at our valence excited states. Okay, and we can say, we can rationalize what's happening is this functional. What it's doing is essentially leaving our valence orbitals alone and essentially affecting the energy of our core orbitals. Okay, and that obviously feeds through into our time-dependent DFT calculation in terms of computing the excitation energies. So how can we go about actually using one of these functionals? So now we're going to return to our formaldehyde problem with a short-range corrected functional. So our input is we had before. Now we're inputting a short-range corrected functional. We input it as a general functional. Here we have to turn on saying we need to perform a calculation with a short-range corrected functional, and we have to define our parameters. And these are parameters which we've determined through fitting to this set of excitation energies. Okay, these are generally inputted. So a 500 here means that essentially you've got 50% Hartree-Fock exchange at R12 is equal to 0, and this is your relative, the corresponding attenuation parameter. And that corresponds to 0.56 per Bohr. Okay, and these are the numbers you get from this. So these are experimental numbers, and you can see that our calculated numbers now are much closer. Remember, B3 lit was giving us a number something like 275 electron volts here. Okay, so by using these functionals, you'll certainly get numbers which are much closer to the experimental numbers, and also we've got some evidence to show that the actual overall profile of your spectrum improves as well. So if we now want to think about a heavier nuclei, and that is now we're going to think about a phosphorus 1s transition to sigma star in the pH3 molecule. And so there's two factors we need to think about here. The first is, for heavier nuclei, we need a slightly different parameterization of our short-range corrected functional. And the second is, we can't ignore relativistic effects. And here I'm talking about scalar relativistic effects. And what these scalar relativistic effects do, the effect they have is to lower the energy of the core orbital. And so what we do at the moment is to essentially estimate this lowering from essentially looking at the orbital energy in a relativistic and non-relativistic calculation. Okay, and these are some rough numbers of how much the energy of the silicon 1s orbital is lowered by relativistic effects, and so we need to include that in our calculations. So here is our input for this calculation for this phosphorus 1s excitation. You can see here these are the different parameters which we use for the second row nuclei, and you can see the key thing is that you have a much higher percentage of Hartree-Fock exchange in the short range. Now, before we had 50% Hartree-Fock exchange, now we have got 87% Hartree-Fock exchange. And so this is the experimental number. This is the number our calculation gives us, and then we have to add on our estimate for the relativistic effect, and then we turn up with a number which is in reasonable agreement with the experimental number. Okay, and you can take this further. You can look at transition. There's a lot of interest in looking at transition metal systems. So these functionals, they do work okay for transition metal systems. We generally see a slightly larger error, but now we've got to really worry about these relativistic corrections. And as I say, at the end, this is somewhere we're working on in terms of Q-Chem. Is now, so this is a copper 1s excitation here. And if you estimate the effect of relativity on the copper 1s orbital, it's about 80 electron volts. So now this relativistic correction is very large, and so if we're going to get accurate numbers here, we have to do a pretty good job on getting that correct, and that's something we're working on. Okay, the final bit of the talk is to think about larger systems. Okay, so one of the reasons why this becomes a problem for NEXAFS spectra is because of the large number of routes you need to compute if you're going to compute this whole spectrum. Okay, so if you want to compute a UV spectrum of something like coronene, then you're probably talking about computing 10 to 20 roots. If you want to compute the NEXAFS spectrum for this molecule, which covers a similar energy range, about 10 electron volts from the absorption edge, you're going to be talking about, you're going to need about 200 roots. Okay, and the reason is, one of the reasons is you've got excitations from lots and lots of core orbitals, and the second is that you see the actual density of these states is much smaller. Okay, so to actually get up to higher energies, you need to include much more of them. The second thing is, once we're dealing with these short-range corrected functionals, we've essentially made the problem worse in that we have got these additional integrals over the error functions which need to be computed. Okay, so the cost of these calculations of short-range corrected functional will be greater than using a standard hybrid functional, and that's true if you use CAM-V3-LIP as well. So what we've done is seek ways to try and make these calculations cheaper. And to cut a long story short, what we've found is you can actually reduce the quality of your integration grid and your 2-electron threshold, integral threshold, within the time-dependent DFT part of the calculation. And this has a surprisingly small effect on the actual accuracy of your answers compared with if you use standard parameters. So let's spell this out. So what we're doing here is we've got this set of molecules and we're computing the lowest, I don't know, 10 or so core excited states at the various edges as indicated. And we use standard grids and integration thresholds. Again, if you look at the Q-Chem manual, you can read all about these types of things in the first part of the cone-sham part of the calculation. So we get good orbitals, good orbital energies. And then once we switch, once we start the TDDFT part of the calculation, we dramatically reduce the quality of our integration grid and our integral, and we increase our integral threshold. So what we do is we turn this grid down to something like a 10-point radial grid and an 18-point angular grid. And now, when I first saw these numbers, I mean, anyone who does DFT calculations would assume that this would give you absolute rubbish using a grid of this quality. And similarly, increasing the size of our integration threshold means that we're actually computing far fewer two electron exchange integrals, for example. But when you actually apply this to these TDDFT types calculations, you actually see that the error you introduce is pretty small. I mean, 0.0 eV, 0.06 electron volts is our maximum error in these excitations, and an average error we introduce about 0.02 eV. And this is really quite surprising, but I don't know, for those of you who are up to date with the TDDFT literature, you might have seen a paper by Stefan Grimmer recently on simplified time-dependent DFT, where he was doing a similar kind of thing in that he was looking at very large valence excited states, but what he showed was really making drastic approximations in how we actually compute the matrix elements in our time-dependent DFT calculation, and actually showing that things held up pretty well. And that's certainly what we found in this sense with these core excitations. So we're getting near the end. So now let's actually think about computing a carbon K-edge spectrum for coronene with a short-range corrected functional. And here we have got input our coordinates. We now set up our short-range corrected functional. This is for our first row elements, so 50% Hartree-Fock exchange. We've got 24 carbon 1s orbitals, so we have to tell it all those. And the only thing I want you to notice is this rem, TDDFT fast, which we turn on to true. And what that will do is we'll reduce change the quality of the grid and the integral threshold for the time-dependent DFT part of the calculation. And this really does speed things up quite dramatically. Okay, and if you wanted to compute the spectrum, I think it said you need about 150, 200 roots. Okay, and this is what you get out. So this is the experimental spectrum, and this is our calculated spectrum. So this hasn't been shifted or anything. This is what comes out of the calculation. You can see it matches up quite well. We can then look at these two peaks here, and you can see that this lower peak here corresponds to exciting from the carbon 1s orbitals, which aren't bonded, for the carbons which aren't bonded to a hydrogen, to the pi star orbital, whereas this peak here corresponds to exciting from the carbon 1s's which are bonded to a hydrogen. Okay, so conclusions and future development. So what you should have got from this webinar is essentially how we can go about computing core excited states. And there's a few things you've got to think about. First of all is essentially truncating the excitation space. If you don't do that, you're not going to get very far, okay, because these excitations at such high energy. If you want to get absolute excitation energies right, then I think the best thing available is these short-range corrected functionals. You're going to, once you go down past the first row elements, to start looking at excitations from things like phosphorus, sulfur. If you want to go into transition metals, then you have to start worrying about relativistic effects as well. If you want to push towards larger systems, then it is a neat trick, this lowering essentially the grid quality and increasing the integral threshold in the TDDFT part of the calculation. I mean, you can test it out for yourself, and you can hopefully see that the error it introduces is quite small, and the speed up you get is quite a lot. So where we sort of would like to push this in the future, I think what we really need is some integrated treatment of relativistic effects, and this is something we're working on. Thinking about this simplification of time-dependent DFT, so this lowering the grid threshold, etc. I mean, is there more work we can do there to get some quite cheap TDDFT setup, which will mean we can study much larger systems, and then also pushing towards thinking about X-ray emission spectroscopy. Okay, so that's where I'd like to wind things up. There's some background reading here if you're interested in these types of functionals and some of the work we've been doing with near-edge X-ray absorption fine structure.
Okay, thank you, Dr. Bassley, for the very nice presentation. We have some questions from the audience. The first question is that in your second to the last slide, in the Cronin example, you showed a comparison between experimental and theoretical spectra. From Q-Chem output, we get discrete spectra. How can one go about obtaining continuous spectra like experiments without having to include dynamical relaxation effects?
Yeah, so that's correct. So the way that I generated that spectrum is to take the transition energies and oscillator strengths, which are given by Q-Chem, and then represent each of the transitions with a Gaussian function, where that Gaussian function, the area under that Gaussian function, is proportional to the oscillator strength. And then I convolute all those Gaussians together to produce the spectrum. And of course, when you do this, you have to choose a bandwidth for your Gaussian functions. And this is I generally choose this such that your spectrum matches experiment. And so typically a value of about about 0.3 to about 0.7 electron volts would be the typical value we would use.
Okay, the next question is, did you get localized or delocalized core 1s orbitals in benzene?
Yeah, so if you do a cone-sham DFT calculation for benzene, you will get delocalized orbitals. So you'll get 6 core orbitals which are made up as different linear combinations of the carbon 1s orbitals. And all the calculations we've done on these things will be based on looking at delocalized core orbitals. It's quite difficult to get localized core orbitals directly from your Q-Chem DFT calculation. We've played around with these things where you have to break the symmetry of your wave function. So if you take, for example, in the benzene case, if you did a calculation where you've got C5 carbon, if you replace one of your carbon atoms in your ring with a nitrogen atom, and then do the ion, so calculate the positive ion, and use those core orbitals as a guess, as a starting point for your calculation on benzene. You can, I've not tried it for benzene, but on similar systems you can force the orbitals to be localized. Okay, and then in principle you could do your TDDF calculation from there. Alternatively, if you really wanted to generate core localized orbitals, I mean, Q-Chem does have things like Boy's localization scheme, which you could use, but personally I've not tried that and looked at the core orbitals for a system like benzene.
Okay, the next question, how does the core excitation energies change with the chemical environment, say from formaldehyde to benzene?
Yeah, so the difference in those energies will be sort of a couple of electron volts. We looked at an example in the talk that really showed sort of the more subtle effects of the chemical environment was to think about coronene. In the coronene example, we see the peak, this intense peak for the first band, which corresponds to exciting to the pi star orbital, or like one of the pi star orbitals. We saw two distinct peaks depending on whether you're exciting from the carbon, a carbon which is bonded to the hydrogen, to a hydrogen atom, or one of the carbons that isn't bonded to the hydrogen atom. And the separation there, I think, was of the order of about 1 to 2 electron volts. And so you can see that very small changes in the chemical environment do show up as splittings in these peaks, which are sufficiently large that experiments can measure. And we've seen that in other systems as well. We looked at some sort of polymer type systems, and we were comparing our computed spectra with the experiments and trying to see where the peaks came from. And you could see distinct peaks from exciting from different carbons or oxygen atoms, where there's subtly different bonding to those things. So in a sense, it is quite sensitive to the chemical environment.
Okay, the next question, did you try short range correct functionals based on PB exchange or correlation?
No, we've only really fitted the functional, which was essentially a modification of sort of B3 lip or CAN B3 lip. I mean, it would be of interest to do these, to try different functionals, and it's certainly something we could think about doing. I mean, part of the reason why we haven't done it is to actually parameterize these functionals. There are these 4 parameters which we need to optimize, and so that's actually quite a wide range, so it's quite an extensive search you have to do to try and optimize these things. But it's something I think probably it'd be worth looking at just to see if we could improve things a little bit.
Okay, the final question. Is the TDDFT_fast feature available in Q-Chem releases?
I think it should be in the most recent releases. So one of the things I'm looking at doing is really extending these ideas to think about sort of TDDFT calculations for valence excited states. I mean, so what I showed was for core excitations, I think you can take to grid down and also turn up the integral threshold to electron cutoff. But I'm not sure how that would hold up if you were doing, say, we're back to our first example where we're looking at the transitions in formaldehyde for the sort of N-pi star N3S transitions. So although that feature is there in Q-Chem, I think if you wanted to use it for valence transitions for large systems, I think you would want to check carefully before you actually used it.
This concludes our webinar. We would like to thank Professor Nick Besley for his excellent presentation. If you've not tried Q-Chem lately, we have come a long way, and we invite you to utilize our 2-month full-featured demo, which you can request by hitting the orange free demo button on our website. Should you have any questions, please feel free to contact us by emailing Lisa Champagne or Levon at the email addresses noted on your screen. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.